Hello, everybody. Thanks for tuning in. I'm Loic Royer, and today I will talk about Iden, our tool for easy denoising for all. First, I'd like to introduce a little bit the team and what we do. We do actually three things. We design and build light sheet microscopes. We also write a lot of code for image processing and analysis. And we use all these technologies to try to answer key questions in developmental biology. We really follow the mantra of Brenner. Progress in science depends on new techniques, new discoveries, and new ideas, probably in that order. And so for that reason, we have developed a lot of technologies, going all the way from automatic fish rearing to light sheet microscopes. We were at the inception of Napari. We do a lot of terabyte scale image processing, but really today, I'd like really to focus on Iden, which is our tool for image denoising. But before, let's motivate a little bit why is image denoising important. You know, our instruments are really limited by the physics and by technology. If you try to go very fast with your imaging instrument, microscope, you'll have to sacrifice contrast or resolution, or both. If you want to have very high resolution, you might have to sacrifice some speed or some contrast. So you can't, it's very difficult to have all these, to push all these dimensions to the maximum. If you change instrument, you can definitely change the envelope, right? If you use a new physics principle, if you use a new technology, you will change that surface, and you will have access to different trade-offs. Another thing you can do also is use algorithms, and to basically turn images that would be perhaps not usable into images that you can use. And the most obvious thing you can do, for example, is to denoise images. And if you do that, then you actually potentially can relax experimental constraints. Now, perhaps you can now image faster. And so you would, by imaging faster, you would have maybe noisier images, perhaps images you cannot use. But now with denoising algorithms, you might be able to actually recover images that perhaps are as good as what you would have acquired with slower imaging, or with more light, or if you had engineered a sample with better signal. So really, denoising is potentially a very, very useful post-processing of your images to actually not just make your images better, but also perhaps to improve your experimental design and basically have access to conditions that you perhaps would not have access to otherwise. So this presentation is organized in three parts. First, we'll go through some theory and intuition on denoising. The second part is an introduction on Iden, what it is, the philosophy of the design, and some examples of denoised images and videos. And the third part will be presented by Amit Solak in my team, who has done a lot of engineering for Iden, and he will go through a step-by-step tutorial and through some demos. First, let's go through the theory and intuition. So, denoising is a particular case of image restoration. And really, the context here is that when you have an imaging system, like a microscope, you essentially use that instrument to access, to observe an image that is not necessarily the image you really would like to have. The image you would like to have is something you cannot have because it's an ideal image. It's the image you would acquire if your instrument would be perfect, or if it would actually break the limits of physics. But you can't do that. Our instruments are imperfect, they are limited by technology, they are certainly limited by physics, and therefore what we observe is much less ideal than what we would hope to observe. And so our images are typically noisy. And that's one kind of problem that can affect our images when we image them. But it's one of the main problems, I would say. And so the inverse problem topic is really concerned with how do we invert that? How do we go from an observation that is imperfect to something that's closer to the ideal image that we would like to have? And so for that, we need somehow algorithms running on computers to basically pseudo-inverse that and then basically get to that ideal image. And in the rest of the presentation, I typically use F to denote the forward model, so the imaging process itself, and G, the function for the pseudo-inverse, which does the restoration, right? And the important thing to notice here is, and to know is that because our instruments are imperfect, this function F loses information. We do not have actually the access to all the information that this ideal image contains. We lose a lot of information, and that is part of the degradation. The question of whether the information we lose matters or not is a different one, and it's actually an important one. But independently of the content of the image, we lose information. If you have an image that is noisy, it actually contains less of the information that you care about, which is the true information in ideal image. Now you also have, in that noisy image, you have content that actually is associated with the noise itself, which is not something you care about. So because of that loss of information, the pseudo-inverse, the restoration, the denoising is difficult, is complicated, because there's a fundamental uncertainty about where, we lose information, and it makes it difficult to go back. And so on the abstract, the way you can think about it is that you start with a space of images, the true images, that is within the space of all possible images. It's a kind of high-dimensional manifold within the very high-dimensional manifold of all possible images. And within that space, which is this blue line here, you have, you can pick a single image, let's call it Y, and then we can consider the forward model, which takes that image Y and observes it. And then we have an observation X, and that observation X is all we have access to, right? But it's part of the space of all possible observable images. Now, what we're trying to do is go back, right? We're trying to go back to the true image Y. The problem is because we've lost information in this forward model because F is losing information. We cannot find a single image Y that would explain X. There's actually a lot of possible Ys that would actually explain what you observe with X. And that's really what I mean by losing information. And this is this space of possible solutions, which I denote as this little curly subspace Y in red here. And of course, the true solution is part of it. So our Y is part of that space of possible solutions, but it's only one among potentially, billions or more potential solutions there. And the true solution is really the solution that is, a true image, and it is also part of consistent and potential and a potential explanation for what you have observed. In reality, the intersection between the blue and the red could be just a single point. It could be multiple of them. But suffice to say that really the problem in its essence is how do we find this Y that satisfies both, that has to be consistent with what we observe, but also consistent with what we consider are the true images, right? And so that's really the problem. How do you find a solution that is the closest possible to Y, the real antecedent of Y in your system? So this is a complex problem, and it's been a very rich topic of research for decades, if not more. And so, there's not just noise. I just want to point out, there's not just noise as a potential degradation of image. You have also motion blur, quantization, optical blur, all sorts of blurs, backgrounds that are superimposed on your images. But again, for the purpose of this talk, I will focus on noise. But I just wanted to point out that the topic, the inverse problem topic is really something that can be applied to many different kinds of degradations of images. So the solutions that people have come up to solve this and to basically, denoise images, deconvolve images, remove motion artifacts of one kind or another. All these problems have been attacked by a series of approaches. The first ones were based on first principles, so very heavy in mathematics. You had to understand, things like regularization. You had to devise iterative algorithms. You had to devise, understand sparsity and how you can use that to, using wavelets and other techniques, how to basically denoise the images. So you had to, the mathematical sophistication of these algorithms were pretty high. And step by step, people have been designing algorithms that are a little bit more data-driven, all the way to deep learning, which is really intensively data-driven. And so really there's this trend towards more data-intensive approaches to image restoration and solving inverse problems versus the first approaches that tended to be more knowledge-intensive. And really the way to understand this is that all these approaches really rely on the abstract prior, which is this space of true images that you're trying to characterize. What is a reasonable solution for the denoising problem? So in the past, in the case of the first, kind of iterative approaches that involved solving some optimization problems, you had to characterize that space. You had to define that prior about the true images as, for example, in the case of TV priors, you would say, the correct images are smooth in some sense, and that would be described mathematically. Or you would say, no, in some space, these images are sparse. So if you lift into some other space through, for example, wavelet transforms or some other transforms, you would find that these images are sparse, and therefore, if they are sparse, that would be the definition of that subspace of true images. But as the field has evolved, what people have realized is that it's very difficult to describe these subspaces of images in a very accurate fashion mathematically on first principles. It's much easier to actually just provide a large collection of images and say, this is the kind of image I want back. And so that's much easier. And so that's why, the field has been moving towards more data-driven approaches, because it's much easier to provide data than it is to actually write very complex mathematical priors. And so that describe what you're actually looking for. And so this has really been the trend, and it's been very interesting to see that happening. When you look at this extreme case of going all the way to very data-intensive approaches, I think the CARE paper from Martin Weigert is a great example, right? Where you provide you use pairs of images, observed and ideal, and then you basically train a neural network to learn from that, and to basically transform the observations into what you ideally want to see. And the way you can do that, how do you obtain these ideal images? You perhaps do an experimental trick. You fix your sample, and you now can take pairs of images at low and high exposure or laser power, and now you can get these pairs of images. And so now, if you have these pairs of images, you can learn which basically simulate in some sense this four model. Now you have the truth, and you can simulate that observation. You can then train a neural network to actually provide you the inverse, and that will take the observation and will give you back the restoration. And it's remarkable how well that works and how powerful these neural networks can be. And it's really because I think it's possible because that prior has been described by a large collection of data, and so just by even though the observations are very poor in information. Because we know really, really well the kind of images we expect to find, we can really powerfully, triangulate in some sense the true images that we really want from very information poor observations, right? So that's very powerful. That's also risky because, of course, there's a lot of imputation happening, right? And so you have to also make sure that your assumptions are correct here. The training data has to really fit what you apply the training models on, and so on. But it's been extremely successful overall. But as I said, yeah, it is powerful, but it cuts both ways, right? This power also has dangers. And so, in 2019, we wrote this perspective where we were looking at the applications, but also the promises, but also pitfalls of deep learning for fluorescence image reconstruction. And we had this example, which I really like, that just highlights a little bit these difficulties. Is an example of an image with a word that is unknown, and we're trying to figure out what that word is by denoising the image, right? So what we can do first is we can simply, use as training data set pairs of letters, not noisy and noisy pairs, so that we can train our neural network using, for example, Latin characters, and we can almost perfectly recover the word, which is an old English word. In this case, vitengnagemot, whatever that means. If we, for example, remove from our training data set a few letters that actually appear in that word, then we will see that actually we cannot really properly recover that word, because now the E's are kind of gone, the A's are gone too, or transformed into something else, and the mistakes are very plausible. If you would not know that your training data is missing something, you would not know by looking at that image here. You would not realize that actually these are not real, because it really looks like a really, really good guess. And it's not the Y here that's replacing the E, or the O that replaces the A, really look plausible mistakes that are really difficult to locate if you have no reason to know that these are actually problems. So that's a bit concerning. But again, it's that's the dangers that come with the power of this approach. Now, if we push it a little further, we say, okay, let's just try to train on Chinese characters and see what happens. And what happens is you still find where the signal is, but now it becomes unreadable. That's kind of expected, but it will give you something back, right? It will give you something back. Definitely, these are not Chinese characters anymore in the image there, but and then you might recognize some of the letters, but definitely that shows that you cannot train on the wrong data, and if it's very wrong, the result is going to be very wrong. That's fine. That's expected. Now, a little bit more interesting experiment is what happens if you actually combine in your training data set both English and Chinese characters. What happens? Well, what's interesting in that case is that now you will actually still be able to sort of read the word, but now you will have additions to that. You'll have some sort of Chinese decorations on some of these Latin characters. And so now it's, what it means, what's surprising here is that you would expect, oh, if I increase my training data set to have more things, it should just be better, right? Because it will know about Latin characters, but also know about Chinese characters. But that's not true, because by increasing your training data set, you also increase the chances for confusion. You give it more chances to confuse things because you have given more things. So it's not always true that increasing the size of your training data set will always improve things. In some cases, you can also increase the chances for confusion. And so that's something to keep in mind, and this is an important consideration, especially when you're using deep learning here for kind of signal recovery. You have to be conscious of that problem. Another thing that people oftentimes ask is, can you really discover something that is not in your training data? Well, yes, you can. Although the training data contains, for example, in the first case, only Latin characters, you still can discover a new word that you never heard about. So it's not because your training data does not contain that word that you cannot now read it when you could not read it before. So that's the point. It's just a matter of the building blocks that you use for kind of training, and how you use that for then discovering something from your data. And so because of this difficulty with the training data and these dangers of confusion and the difficulty to actually make sure that the training data perfectly matches what you applied on, it would be great if we would not actually need to have this ground truth, right? It would be great if the training data is not something different from the data you're actually trying to denoise, or essentially the image that you're trying to denoise should be all you need to denoise it, right? That would be a better situation, right? No need for these clean images. We just have an image, it's noisy, and we want to denoise it. And we still want to use deep learning, and we still want to have great results. And it turns out it's actually possible. With Josh Baston, when he was at the Biohub, we worked on this problem, and then we found a very nice solution for that. And we call noise to self, which is a way to do self-supervised denoising, blind denoising, using deep learning. And actually, in our paper, we worked out a general theory. This was actually this idea of noise to self was actually found by others, such as the team of Florian Jung at the time in Dresden, and essentially the same idea. In our case, we extended the idea to any denoising algorithm and came up with a kind of generic theory. And this generic theory we call the theory of J invariance, which is quite involved and basically says that for any given denoising algorithm, we have a way to discover the best sets of parameters so that the algorithm, the denoising algorithm, can denoise images in the best possible way. So we have a way, essentially, we have a way to tune the meta parameters or parameters of a denoising algorithms perfectly without any ground truth, right? So that opens up a lot of opportunities. I will not go into the details of the theory because it's a talk on its own right, but I will try to convey the intuition of how noise to self works. So here's a game. Can you guess the true intensity of the red pixel in this image? I'll let you think a little bit about it. Pick your guess. And I guess you can try to use not just the red pixel, of course, because that doesn't carry any information because I'm hiding what the real pixel value is, but you're probably using something around it, right? Some of the pixels around it. And so if you are good at guessing, you would have probably guessed that this is probably the most likely color of that pixel. And the question is really how you've done that. As I said, probably by looking not at the pixels around that pixel, and this is really the key, because of course, we know something by looking at this image. We start to understand things about this image. We understand the structure, even if you don't know about what an eye looks like. You will still understand that there's some regions of the image that are darker, other regions that are brighter. There are some relationships. If this is part of a much larger image, you might be able to gather some insights about how eyes typically look like. And so we have ways to even from a single image to basically infer the color of that pixel that I've been hiding here. And so if you actually play that game again and again on each pixel, and if you replace each pixel by the best possible guess you can make about what that pixel value should be, and every time, of course, you're not aware of that pixel value, just hide every pixel and try to guess as best as you can what that pixel value would be on the basis of its context. If you do that for every pixel, lo and behold, you actually denoise the image. And it's a very simple idea, right? It's a simple game. Replace each pixel in the image by the best possible guess of that pixel value on the basis only of the context. And so this principle is really the basis of Iden and of all the algorithms in Iden. Because what we've done is we essentially have lots of different algorithms in Iden, and we have applied this chain variance theory to be able to tune all their parameters, be it the millions of parameters of a neural network or the few parameters of a median filter. And so we basically have applied this, and now we have this tool, Iden, that is very powerful and that can denoise images in a variety of ways. And so I will go through in this next part through a little bit of an introduction about what this tool is, its philosophy, and some examples. And so really the starting point of Iden was like, okay, we have noise to self. How can we make this magic fast and easy to use and for all? And so, we brought together a team, which at the inception was made of Amechan Solak, Hirofumi Kobayashi in my team, also a postdoc, Josh Baston, who was at the time at the Biohub and who was the first author on the Noise to Self paper, and myself. And we started coding, and we did a lot of coding, I must say. And the result is a very complete tool with a very rich graphical user interface, lots of parameters, lots of kind of built-in documentation in the tool, lots of options and ways to denoise images and ways to deal with the complexity of images in microscopy and in science in general, multiple dimensions, the need for cropping, and so on and so forth. It's a long story. We have a lot of documentation. Actually, in the third part, Amechan Solak is going to go through all of that and through a demo for you. But the important thing at this point to understand is that we don't just have a very nice user interface and application that you can download as a standalone. We also have, which is something that's really easy to use. So it's the maximal ease of use kind of pattern of usage that we propose. We also have other ways to use Iden. You can use it on the command line to run large jobs, and you can basically use models that have been trained using this Iden Studio UI. But we also have for the coders out there in Python, a programming interface so that people can actually use all these algorithms within their own tools or scripts or packages or whatnot. And so really we have that spectrum here from very easy to use on one end, but perhaps a little less flexible in some aspects in terms of programmation or command line interfacing, and on the other way you have the full flexibility of a programming interface, but then that requires a little bit more kind of expert knowledge to use. And so I said before that Iden supports a large number of denoising algorithms, and the reason is because we really believe that, there's not a silver bullet that fits all denoising problems. So we wanted to have lots of ways to denoise images. And so we started, of course, with the noise to self approach, which is basically based on CNNs on the UNet. We added other variants of this, especially particularly our GINET, which is a sort of a UNet that has been modified to actually be capable of training faster. But we also have played a different game, which is instead of using CNN, so deep learning, we also use a kind of classical machine learning where we generate features from images and then we do regression and use that to actually denoise the images through the same theory as noise to self. So that's another way to do that. But we also were interested, as we actually hinted and showed a little bit in the noise to self paper, at looking at classical denoising algorithms and see how much we can improve them. So we have dictionary-based algorithms, but also low-pass filtering algorithms, especially Butterworth, which is very effective, or Gaussian filtering. And we have a bunch of other classical denoising algorithms. But the key thing here is they're all auto-tuned with noise to self. So if they have any parameters, we basically used the noise to self theory to basically be able to find the best parameters. And what's really interesting with that is when you do that, you realize that actually some of these classical denoising algorithms are really good. It's just that we really didn't know how to tune them well. And in some cases, they actually are pretty competitive with machine learning or deep learning based noise to self implementations. And so that was actually an interesting observation, and this is something we will be giving more detail in the preprint, the upcoming preprint. But yeah, so this is very interesting to see that actually you can actually get pretty good performance and sometimes dramatic speedups. And so we now with this set of algorithms, we can explore a large spectrum of compromises between speed, performance, how much hallucination you want to have or you want to tolerate, how much so many considerations that you can modulate when you choose your denoising algorithm. One key important thing here is that to notice that there's definitely still this good spectrum, this gradation between data intensive and knowledge intensive algorithms. It's still there, and that's another reason why you want to have that diversity, because in some cases, if you know something very well about your imaging system, you might not want to throw away that knowledge. You might want to actually use that knowledge to actually pick an algorithm that is ideal for your imaging system. So really, when one asks the question, okay, which algorithm is the best? That question doesn't really make sense, because you need to know a lot of things to answer that question. You need to know, okay, what is your instrument characteristics? What do the images look like? What's the content of the images? Is it sparse? Is it very uniform? Do you have high frequencies in your images? Do you have low frequencies? What is, there's so many characteristics of the instruments that acquire the image, of the thing that you're looking with the instrument. There's so many things to consider that actually the better question is perhaps which algorithm to choose for the images coming from your instrument. And so, again, that's why that diversity of algorithms in our experience has been more useful than just trying to find the one algorithm that solves everything. We have not found that algorithm. What we found instead is that it's better to have a multiplicity of algorithms that provide different performance profiles, different speeds at processing the data, and different trade-offs essentially and also different characteristics that make it more suited to one kind of image or another. And so As an example, why sometimes you cannot just simply pick the latest thing and hope it will always be better. Here are some images from the team of Jean Longmaître at Curie in Paris. These are mouse embryos imaged with a spinning disc confocal microscope. So on the left you have the raw images. On the middle you have that image denoised with our CNN-based noise-to-self implementation, and on the rightmost panel we have Aydin's auto-tuned low-pass filter, which is Butterworth based. What's very interesting is that you might not want to use CNNs for that because they are actually, have issues with anisotropic images that have resolution much worse in one direction than another. There's sometimes also over-blurring because of some of the aspects of how the CNNs operate. You also have oftentimes hallucination risks because, of course, the CNNs are very powerful at giving back something that looks okay when it's actually a pure hallucination. And the biggest problems, for me at least, is the training times that are sometimes are really prohibitive. And when you compare the result you get with that compared to more a simpler and perhaps more physics-based approach, which is simply a low-pass filter that is automatically tuned using our noise-to-self theory and chain variance theory, we can actually denoise images much faster, 30 minutes instead of 3 minutes instead of 30 minutes, so 10 times faster. And because it's it's a physics-based denoising, hallucinations are impossible. The thing here is that if you would not know exactly what frequency is your cutoff frequency at, it might be difficult for you to find the perfect way, the perfect parameter to tune that denoiser. But we take care of that with that theory, so we can figure out automatically what's the best parameter for denoising here. And that's what gives these approaches, these more classical approaches, a bit of an edge, at least on the practical standpoint in terms of speed, but also in terms of lack of dangers from hallucinations or any other sort of things. So perhaps on much harder images that are much more noisy, it would be better to use CNNs. But in this particular case, for this particular image here, turns out not necessarily. So, and again, it's all trade-offs, right? Maybe if you train for a very, very long time, perhaps you can manage to get, better images than what I'm showing here. But it's all about, this general performance envelope of, how practical it is and so on and so forth. So, and the hallucination risks, are still, something that will always remain a danger with CNNs. And so, with other kind of approaches that cannot hallucinate, that you have an inherent safety there, that you can have if you need it. As I said, we don't have, I don't think there's a best algorithm in general. It's always relative to the data and the instrument and the particularities of your problem, and also of the downstream processing tasks that you might have. But we do have our favorites in Iden. We do have our favorite algorithms, and definitely for us, this auto-tuned low-pass filter is really one of our first go-to algorithms because it's really fast, it's really safe. But does have issues with sometimes a little bit over blurring, and also has issues with background. It cannot really suppress uniform background regions properly. Our next kind of the other algorithm that in Aydin that we really like and that we often use to show when we show demonstrative videos is this FGR cat boost algorithm, which is essentially noise to self using machine learning. We generate features and we use regression, and we basically use that to actually denoise images. So it's a different take on noise to self, but it's actually, it has the advantage of being very fast. It's not as fast as some of the classical methods like low-pass filtering, auto-tune low-pass filtering, but still pretty fast, 7 minutes in this case. It's definitely able to take care of anisotropy problems. It understands the anisotropy of images. It has great performance for background. You look at this background; is really uniform, very clean. It also produces images that are really sharp and well contrasted when you compare them to the original or to some other approaches. And it's definitely in our experience and with the evidence we have collected, definitely much less susceptible to hallucination. And that's also perhaps because it is actually less powerful at imputation than CNNs. But the truth is that perhaps neural networks are not, perhaps denoising is not necessary, in most cases, is not so complex a task that it requires the power of CNNs. So that's kind of the little bit the argument we have here, is that perhaps there's a middle ground here where you can have methods that are actually a little bit safer but still very powerful and also much faster. And another big advantage of this method here is really something, the reason why I just always go back to it when I need to denoise images for my own purpose, is that there's very little stochasticity in the training, and so we always get the same result almost. Which is not the case with CNNs. With CNNs, you have stochastic training. Sometimes you land in a weird area of your loss landscape, and then you basically have some weird denoising, and so you never know if your first training run is actually going to be the one you can actually use, and that's really annoying with CNNs. But with our FGR approach, we rarely have that problem. It just always goes to the same solution. And that's a very, very nice feature from a practical standpoint. Iden is fast, as I've said, and so we have some more examples here. Here is an example image. These are 30 dpf zebrafish larvae, standing in Stapi. We image that with a spinning disk. This was acquired by Shruti and Vijay Kurmer and Merlin Lange in my team. And then so it's a fairly large 3D stack, multi-channel, and the training is just barely 4 minutes, and the denoising is 3 seconds. So for all practical purposes, just need 4 minutes to denoise that image, and that's done on a laptop without a GPU. Okay, so that's really good. Definitely very fast. Here are some images of carbon nanotubes in solution from our collaborator lab from Laurent Cognier in Bordeaux at LP2N. So these are acquired on a wide field microscope. These are carbon nanotubes in solution. The image size is 1000 by 320 by 320. So a really very large image by any standard. And again, we just need 5 minutes for training. And the denoising itself is just 1.3 minutes. This is done on the laptop with GPU, and then we can basically get beautifully denoised images where really you literally do not see anything. You can't see anything in the raw image, but then when you denoise, you can see where these carbon nanotubes are. So Iden works also for very low signal images. Another example where the data is very noisy is typically found in 2-photon calcium imaging. Again, a fairly large 3D stack, 128 by 512, 512. And again, on a laptop with GPU, you can train a model for denoising, an Iden model for denoising, in less than 2 minutes, and then in 36 seconds you have the image denoise, or you could even denoise more of such similar images in, again, just 36 seconds. So it's really fast. And as you can see here, the performance is really remarkable here. It's extremely noisy. And now you have a situation where you can almost resolve some of the processes of these neurons. So it's really a very nice result. But it's not just about getting pretty images or pretty videos. It's also about facilitating the downstream processing tasks. That's really one of our main motivations, of course. And so, thinking about two-photon mouse brain calcium imaging, we have here data from our collaborators at Harvard, Richard Hakim from who acquired these images from the lab of Bernardo Sabatini. These are very, very nice data sets, and when we applied, our tool on these images, the result of the denoising was really stunning. I was really stunned by the result because it's really day and night, contrast here between what you see in the original raw data and what happens now when you denoise. So it's really a remarkable result here, and it's really. It's really a powerful way to process the data, because then if you do that, if you actually use, for example, Sweet2P to identify the neurons in this image, which is something that Merlin Lang and my team did for demonstration purposes of Iden, we can clearly see that after denoising we can identify much more neurons in this data. And so that's really, it just really shows that if you denoise your data up front, you can actually potentially facilitate your downstream processing. Similarly, in my team, we have been working on some projects involving zebrafish embryos. We've been doing some DAPI stainings of the nuclei for some purpose, and then my team. This is work from Shute Vijay-Kumar and Merlin Lang in my team, and Giordano Bragantini in my team, who does a lot of our segmentation work on these images, was really having a hard time segment these images, obviously. The result was extremely noisy and extremely difficult to interpret and post-process after that. But although the images are still challenging to analyze, after denoising, the situation was much better. If you look at this region here highlighted within that red square, clearly you can actually see more segments and they are better delineated. So this was really helpful to be able to analyze our data. So this was kind of definitely a use case in our lab of Iden, and the biologists in our team have been extremely happy to use that. And they've been using it for all sorts of purposes, and that I can't talk about today. But it's been extremely exciting, not just to produce a tool for others, but also to use it for ourselves, of course. And so we did all this because we were excited about denoising and the possibilities that open up by doing this. But we also wanted to make sure that we made a tool for all of you to be able to use. And to make it, and therefore we try to make it as easy to use as possible, as fast as possible, because we don't want you guys to wait hours or days for denoising your images, and then we really made sure to share it with all of you, and this has been a lot of work from actually Ahmed Chan Solak in my team. He has put a lot of work on design a very nice user interface and make sure that the app is actually downloadable in different operating systems and usable on different systems, and he wrote a lot of documentation and you can find all of that information, and as well as a lot of use cases that we wrote, so that we explain a lot of things about different ways to denoise our images with Iden. So a lot of information, and this is all accessible on our webpage at iden.app. And in the next part of this presentation, in the last and third part of this presentation, Ahmed Chan Solak is going to go through that website a little bit, show you what's there, and go through some examples and demos of how to run Iden.
Here I will be giving a tour of our webpage, which you can find at royerlab.github.io/Iden. In our welcome page, you can find links to the executables we prepared for different operating systems. Also, some details about system requirements and how you can navigate this documentation page. as well as if you find Iden useful, how you can cite it. In the install page, we go in detail how one can install our executables on different operating systems. Some of them comes with installers, some of them comes as portable executables. Also, we give some details about how one can install Iden with CUDA support. Speaking of CUDA support, Iden implements many denoising algorithms with out-of-the-box GPU support. It is important to note that we mostly test our algorithms with the latest and newer GPUs. Still, older graphics cards could be possibly working with Iden. They may cause some trouble or they might be a little slower, but we are always happy to help if you face any issue. In our documentation, we have also written use cases where we investigate a dataset in detail and how we would go and use Iden and denoise those images and make sure we're getting the best out of Iden package. Let's look into one of the examples that we have written with our collaborators' data from Paris. In a use case, typically you can find details about the data set we are using, also how we are approaching to the image. You will see some zoom ins to certain details, as well as you will see how some of the other features like pre and post processing as shown on the screen can help to the denoising performance, and how one can decide which processing to use on which occasion. Also, sometimes on use cases, we add some explanation on how to interpret our logs, which can be pretty helpful. Also, we expose many configurable options on our Iden Studio GUI. It's sometimes challenging to know what to choose. In our use cases, we try to explain as much as possible how making different choices with these configurable options can affect the denoising performance. Also, we show the final results as well as our observations along the way. We also wrote tutorials for our different interfaces that we provide with Iden. We have provided detailed tutorial on how to use our GUI and different features that it can help to you on managing your data and denoising it, as well as some tutorial on the Iden command line interface that we basically allow the entire configurability that we expose on the graphical user interface. Also, some tutorials on the API that we provide to the programmers out there who might want to integrate some self-supervised denoising into their applications. Please reach us on github.com for any bug report and feature requests. Also, please reach us on image.sc for any usability concerns and questions. Thank you. Let's download a publicly shared dataset and denoise it with Iden. We will be using LimeSec test dataset that is shared on Zenado under Creative Commons license, and we are going to download the Drosophila egg chamber data that we are interested in. It will download pretty quick, it's a small dataset, and then I will be opening Iden window and I will drag and drop the image that I just downloaded. This will load the data into the application, and with the help of Training Crop tab, I'm able to browse the image that I just downloaded. As I'm realizing this is a 2-channel dataset, with the help of Files tab, I will be splitting the channels, and then with the help of Images tab, I will be selecting only the second channel for denoising. And as you know, Iden is a self-supervised denoising tool, and our data sets sometimes can get bigger, and if we want to use all the data we have for training models, that can take a lot of time. So to avoid that, I will be selecting a crop of the data that will be used for training, and I will make sure we will be in the end still denoise the whole image, so the entire image will be denoised. And then I will be selecting noise to self FGR cat boost algorithm, and then I can start denoising. Now the training is completed, and a Napari window will pop up with the resulting denoised image. And we can just toggle off the training crop, which is just a small crop of the image, and then we can actually observe the result of the denoising together with the noisy image. To investigate the results further, I stack up the denoised and noisy layer on Napari window, and with help of Napari canvas, I can pan and zoom around my image, and I can see on different parts of the image how denoising have performed. I like usually looking at different parts of the image to make sure denoising not only worked for certain features in the image or for certain part of the image, but basically it worked well all around the image. And this is basically just toggling the top visible layer in Napari so that I can see the noisy image and then I can see the denoised image. With the help of hundreds of available plugins, also one can continue with downstream analysis of their images and compare how denoising helps their downstream analysis pipelines. Also, one can find the denoised image together with all the configurations that is used to train the model together with the trained model file right next to the input file in the file system.